the molarity of the acid in the burette is 1.24 molars. So here is my message to you. In the rush of trying to hurry up and solve this problem on the actual day of the AP Chemistry exam, you're given a titration experiment and you pick the wrong volume or the wrong concentration. So with the titration experiment, when you set up your calculation, make sure to put the correct volume with the correct molarity. So now I'm going to do this correctly. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 8.4 and 8.5. As you can see on this slide, these topics fall under Unit 8 in the AP Chemistry curriculum, Acids and Bases. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 8.4, Acid-Base Reactions and Buffers. The following is a summary of the essential knowledge statements from the AP Chemistry course and exam description. So we're going to take a look at 4 different types of acid-base reactions, and the first category, or the first type of acid-base reaction to consider, is strong acid plus strong base. So when a strong acid and a strong base are mixed, they react quantitatively in a reaction represented by the following equation: H plus OH minus to produce water. And the pH of the resulting solution may be determined from the concentration of the excess reagent. Our next category of acid-base reaction is weak acid plus strong base. So when a weak acid and a strong base are mixed, they react quantitatively in a reaction represented by the following equation. So now instead of H plus, we write HA. That's to represent the molecular formula of that weak acid. And so because a weak acid is only partially ionized in aqueous solution, then we write the formula of a weak acid as HA, or whatever that formula happens to be, in a net ionic equation. So we still see hydroxide as a reactant to represent the strong base. And then on the other side of the equation, in addition to the water, we see A minus. So A minus represents the formula of the conjugate base of that weak acid. And so we have 3 situations. If the weak acid is in excess, like for example, what would happen in the early part or the middle part of a titration before you get to the equivalence point, then a buffer solution is formed. And the pH can be determined from the equilibrium constant expression, Ka. Now, suppose that you get past the equivalence point in a weak acid strong base titration. So if that happens, if the strong base is in excess, then the pH can be determined from the moles of the excess hydroxide ion and the total volume of the solution. But what if you are at the equivalence point in a weak acid strong base titration? Well, if they are equimolar, in other words, if you have arrived at the equivalence point of the titration, then the slightly basic pH can be determined from the equilibrium represented by the following equation, where A minus, the conjugate base, reacts with water to produce HA, and then there's a little bit of hydroxide ion formed as well, which is why that solution would be slightly basic at the equivalence point in a weak acid strong base titration. Our next category of acid-base reaction is the following: weak base plus strong acid. So when a weak base and a strong acid are mixed, they will react quantitatively in a reaction represented by the following equation. So now we represent the weak base as a capital letter B to represent the molecular formula of that weak base, such as ammonia or whatever that weak base happens to be. It's now reacting with the strong acid, represented as the hydronium ion. And on the right side of the equation, in addition to water, we also can see the conjugate acid of that weak base, which is represented as Hb+. So again, different scenarios for a weak base strong acid titration. If you are in the early stages or the middle portion of the titration before you get to the equivalence point, then the weak base is in excess, a buffer solution is formed, and the pH can be determined from the equilibrium constant expression Kb. Well, if you are past the equivalence point, so in other words, if the strong acid is in excess, then the pH can be determined from the moles of the excess hydronium ion and the total volume of the solution. Well, what if you have arrived at the equivalence point in a weak base strong acid titration? Well, now, if they are equimolar, then the slightly acidic pH can be determined from the equilibrium represented by the following equation. So you can see that the conjugate acid, Hb+, in solution reacts with water to produce the weak base B, and then there's a little bit of hydronium ion produced, and that's why the solution is slightly acidic when you arrive at the equivalence point in a weak base strong acid titration. And then, as you can imagine, our last category would be weak acid plus weak base. So when a weak acid and a weak base are mixed, they will react to an equilibrium state, whose reaction may be represented by the following equation. So we can see that the weak acid, represented as Ha, reacts with the weak base, represented as capital B, and then on the right side of the equation, you can see the conjugate base, A-, and you can see the conjugate acid, Hb+. Now, in topic 8.4 in this packet, during our practice section, we will take a look at all of these four types in terms of the examples and the practice questions. So now it is time to move on to the practice for topic 8.4. This is question 1. In question 1, it says a solution is prepared by combining 200 milliliters of 0.40 molar perchloric acid, HClO4, with 300 milliliters of 0.30 molar potassium hydroxide, KOH. Part A says write the balanced net ionic equation for the acid-base reaction that occurs between perchloric acid and potassium hydroxide. Now, back in topic 8.2, pH and pOH of strong acids and bases, you learned that there are 6 strong acids to be memorized for the AP Chemistry exam. And on that list of 6 strong acids is perchloric acid, HClO4. And in general, a metal hydroxide, where the metal is in group 1 or group 2 on the periodic table, and potassium is in group 1, that's a strong base. So HClO4 is a strong acid, KOH is a strong base. So there's HClO4, but because it is a strong acid and is 100% ionized in aqueous solution, then we're going to split it up into separate ions. So H+ and ClO4-. And for the strong base, potassium hydroxide, same thing. Instead of writing it as KOH, because a strong base is soluble in aqueous solution and would be split up into potassium ions and hydroxide ions, then I will write that as K+ and OH-. Now, the H+ from the strong acid reacts with the OH- from the strong base to produce water. And then what about the rest of the ions? Well, that would be potassium and perchlorate. Now, potassium perchlorate is an aqueous substance. It's an aqueous ionic compound. And you might remember that potassium is one of the soluble SNAP ions, where SNAP, sodium, nitrate, ammonium, and potassium, those are soluble in ionic compounds. So we're going to split that up into K+ and ClO4-. As you can see, we're going to cross off some spectator ions that appear in identical form on the left side and the right side. So perchlorate, or ClO4-, I can cross that off on the left side and the right side. Potassium, K+, I can cross that off on the left side and the right side. And then what I have is now the net ionic equation for the reaction between a strong acid and a strong base, which is what I had mentioned in topic 8.4, H plus OH minus to make H2O. That's how you write the net ionic equation when you have a strong acid and a strong base reacting together. So there's the answer to part A. Let's go ahead and move on to part B. Now, with part B, we have to calculate the number of moles of the following substances present in each solution before the solutions are combined together. Now, to get the number of moles, we will take volume times molarity. So the first part of part B is about the perchloric acid, and then the next part is about the potassium hydroxide. So volume times molarity is moles, as long as your volume is in liters. So 200 milliliters, when you divide by 1,000 to go from milliliters to liters, that becomes 0.2 for the volume in liters. And then 0.40 molar, I'm going to write that as a conversion factor, so 0.40 moles of the perchloric acid for every 1 liter of solution. So what am I doing when I pick up my calculator? To calculate the number of moles of perchloric acid, it would be 0.2 times 0.4, which is 0.08, and I'm just showing two significant figures for my answer. So 0.080 moles of perchloric acid. We're going to do a similar calculation, volume times molarity is moles, for the potassium hydroxide. So now it's going to be 300 milliliters divided by 1,000 to go to liters, so that would be 0.3 for the volume in liters. I have 0.30 moles of potassium hydroxide per liter, so when I pick up my calculator, it will be 0.3 times 0.3, which is 0.09. Again, I'm showing two significant figures for my answer. So we have now answered part B, 0.080 mole of perchloric acid, 0.090 mole of potassium hydroxide. In part C of question 1, we have to determine the pH of the combined solution, which is 200 plus 300, or 500 milliliters. So how do we figure out the pH? Well, remember that a strong acid is essentially H+, so I'm just showing H+ because of the strong acid, and a strong base is essentially OH-. I just rewrote those same values as 0.080 mole of H+ and 0.090 mole of OH-. Is the pH exactly 7? No, the pH is not exactly 7 because we have a slight excess of the hydroxide ions. Well, how much extra of the hydroxide ions do we have? Well, 0.09 minus 0.08 is 0.01. Now, at this point in the stress or the anxiety or the rush of taking the AP Chemistry exam, some students are about to make a mistake. They're so close to answering part C of this question, calculate the pH of the combined solution, that they are going to make a mistake because they pick up their calculator and they take the negative log. Now, if you take a look at that, POH is equal to the negative log of, and it's not the number of moles, it's actually the concentration. So what the student would have done incorrectly if they did negative log of 0.010 is that they're taking the negative log of the number of moles when instead they should take the negative log of the concentration. So what's the concentration? Well, that would be moles divided by liters. What's the total volume? 500 milliliters, or half a liter. So the concentration of the hydroxide ion is actually the pH of the resulting solution may be determined from the concentration of the excess hydroxide ion. So not the number of moles, but the concentration. 0.01 divided by 0.5, which is the number of liters. So 0.01 divided by 0.5, we get 0.020. That is the concentration. And when you take the negative log, be careful. You're not done yet. We want the pH, and POH and pH are not the same thing. So while I have 0.020 molar for my concentration of hydroxide, I need to negative log that number and then do 14 minus that value. So here comes the answer to part C. We have already corrected the mistake. We're not taking the negative log of the number of moles, we're taking the negative log of the concentration. So negative log of 0.020, which is the concentration of hydroxide, is 1.70. Keep going. You're not done yet. That's the POH. So 14 minus 1.7, there it is. Okay, so the correct answer to part C of that question is 14 minus 1.7 is 12.30. So again, watch out for those mistakes of don't take the negative log of the number of moles, take the negative log of the concentration, and if you take the negative log of the concentration of hydroxide ions, that's not the pH, that's the POH. So 14 minus POH is pH. All right, well, there are all of the answers to parts A, B, and C for question 1. So now it is time to move on to question 2. In question 2, it says acetic acid, which has the chemical formula HC2H3O2, ionizes according to the equation above. A solution is prepared by combining a sample of acetic acid with a sample of sodium hydroxide, NaOH. So part A of this question says write the balanced net ionic equation for the acid-base reaction that occurs between acetic acid and sodium hydroxide. Now, are we going to see another example of a strong acid reacting with a strong base like we saw in question 1? No, acetic acid is not on your list of 6 strong acids. So therefore, acetic acid is a weak acid. But we do have a strong base. Sodium is in group 1, just like potassium. So sodium hydroxide is another example of a strong base. Now, what do we do with a weak acid? Well, as you can see here in topic 8.3, weak acids, only a small percentage of the molecules will ionize. So we write that formula of the weak acid not as H+, but as the entire molecular formula of that weak acid. So I am not going to split up acetic acid into H+ and C2H3O2-. I'm going to leave it intact as one molecular formula. So a weak acid, HA in general, is only partially ionized in aqueous solution and should be represented as its chemical formula in a net ionic equation. What about the sodium hydroxide? Strong base, go ahead and split it up into Na+ and OH-. So a strong base should be represented as separate ions. Now, if you're wondering about the sodium ion, it is possible that that will get crossed off as a spectator ion. Let's go ahead and keep going. On the right side of the equation, we're definitely going to have some water. And the reason why we have some water is because the hydroxide ion reacts with the H+, pulling that H+ off of the molecule of acetic acid to produce water. So even though acetic acid is classified as a weak acid, it is still a Bronsted-Lowry acid. It behaves as a proton donor. So the H+ ion is now reacting with the hydroxide to form water. What about the sodium ion and the acetate ion? Instead of writing sodium acetate as one ionic chemical formula, we will go ahead and split it up into Na+ and acetate, which is C2H3O2-. So again, sodium is one of those soluble snap ions. Sodium acetate should be represented as separate ions. Aha, there's that spectator ion that I mentioned. So on the left side of the equation, we have Na+. On the right side of the equation, we have Na+. And now what remains after I cross off the spectator ions is the net ionic equation. Now, if you're wondering, have I seen that earlier in this lesson? Yes. So back in the essential knowledge statements, Ha plus OH- to produce water and A-, that is the net ionic equation when a weak acid reacts with a strong base. So you can see the similarities between the answer to part A of question 2 and what I had mentioned earlier for the weak acid strong base net ionic equation. All right, well now that is the answer to part A. Let's move on to part B. It says in a certain experiment, a 50 milliliter sample of 0.40 molar acetic acid is combined with a 50 milliliter sample of a 0.40 molar sodium hydroxide solution. Assume that the volumes are additive, which means 50 plus 50 is 100. The resulting solution has a pH that is greater than 7. The acetate ion, C2H3O2-, behaves as a weak base according to the equation shown below. So we're looking at the net ionic equation for the acetate ion reacting with water to produce acetic acid and hydroxide, and there is a Kb associated with that, the base dissociation constant. And so in part 1 of part B, it says calculate the value of Kb for the acetate ion. Now we are given the value of Ka for acetic acid, which is 1.8 times 10 to the negative 5. So you might be wondering, is there a relationship between Ka and Kb? Yes, so back in topic 8.3, for any conjugate acid-base pair, the acid ionization constant, Ka, and the base ionization constant, Kb, are related by Kw according to this equation, which you can see on the AP Chemistry equations and constant sheet. So if Kw is equal to the product of Ka times Kb, then if we know Ka, we can solve for Kb. So the Kb is equal to the Kw divided by the Ka, and the Kw is 1.0 times 10 to the negative 14, and the Ka for acetic acid is 1.8 times 10 to the negative 5. So if I take my calculator and do 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, then I get the answer to the first part of part B. So the Kb for the acetate ion is 5.6 times 10 to the negative 10. Now let's move on to the next part of part B. It says calculate the concentration of the acetate ion in the combined solution. So what exactly is the combined solution? Well, there was 50 milliliters of 0.40 molar acetic acid, and there was 50 milliliters of 0.40 molar sodium hydroxide. First, let's figure out the moles of each of the reactants, and then we can determine what happened to produce the acetate ion. So I'll do volume times molarity like I did in question 1. So volume of 50 in liters is going to be 50 milliliters divided by 1,000. That's going to be 0.0500. So there's my volume in liters, 0.05. I'm going to write molarity as a conversion factor. So times 0.40 moles of acetic acid for every 1 liter of solution. And when I pick up my calculator to get the number of moles, just to get started here, 0.05 times 0.4 is 0.02 for the number of moles of acetic acid. You'll notice that we have the same volume and the same concentration for sodium hydroxide. So 0.05 liters times 0.4 moles of sodium hydroxide per liter, we get the same number, 0.02 moles of sodium hydroxide. And how did they react, as you saw in the net ionic equation in part A of this question? All of the acetic acid has now been converted into the acetate ion because we had equimolar amounts of the weak acid and the strong base. So all of the acetic acid is converted into acetate ions. How many moles of acetate ions do we have? 0.02. What's the concentration? Moles divided by volume. Now, what is the total volume? Assuming that the volumes are additive, it's 50 plus 50 is 100, but that's 100 milliliters or 0.1 liters. So if you take a look, I did concentration as moles divided by liters. How did I know that there were 0.02 moles of acetate? Because all of the moles of acetic acid have been transformed into moles of the acetate ion. And then how did I know that the volume was 0.1 liter? Because it was 100 milliliters as the total volume. So 0.02 moles of acetate divided by 0.1 liters gives me 0.20 molar for the concentration of the acetate ion. Now, there is one more part in part B. Let's go ahead and move on to that part. Calculate the pH of the combined solution. Now, we know that this is going to be greater than 7 because the acetate ion is a weak base. If you look at the very top of this slide, you can see the net ionic equation for what acetate does when it reacts with water. And so that's going to be the Kb expression that we're going to write. So the Kb expression, as you can see on the equation sheet, is the weak base on the bottom, and then the hydroxide ion and the conjugate acid on the top. The weak base on the bottom, and then the hydroxide ion and the conjugate acid on the top. So what is our weak base on the bottom? Acetate. What goes on the top? Hydroxide and the conjugate acid. So what I'm showing you at the bottom of this slide is essentially the equilibrium constant expression for the net ionic equation that you see at the top of the slide. And why are we doing this? To calculate the pH of this solution. Now, do we know the value of Kb? Yes, we got that from part 1 of part B. Do we know the concentration of the acetate ion? Yes, we got that in part 2 of part B. Do we know the concentration of hydroxide? Not yet. Let's go ahead and just call that X. So on the top part, it's going to be X times X because I don't know what those numbers are. On the bottom, it's going to be the concentration of the acetate ion, which we've already calculated in part 2 of part B. And then the 5.6 times 10 to the negative 10, that's the value of Kb, which we had calculated earlier. Let's go ahead and solve for X. Now, if we solve for X, that's going to be the concentration of the hydroxide ion. Remember, if you get the concentration of the hydroxide ion, it's going to be negative log to get the pOH, and then 14 minus that value to get the pH. First, let's solve for X. So X squared is equal to 0.2 times 5.6 times 10 to the negative 10. X squared is equal to 1.12 times 10 to the negative 10 when I did that math on my calculator. X, which is equal to the concentration of the hydroxide ion, is the square root of 1.12 times 10 to the negative 10. And when I did that on my calculator, I got 1.06 times 10 to the negative 5 molar. So I've got my concentration of hydroxide. I'm 2 steps away from determining the pH. Negative log it, 14 minus it. That's what we have to do. I'm kind of running out of room on the bottom of this slide. Let me just go ahead and push some of these numbers upwards a little bit. There we go. All right, so negative log it, 14 minus it. So the pOH is the negative log of 1.06 times 10 to the negative 5. And this is not my final answer. This is approximately 4.98. Let me do 14 minus that value, and I get approximately 9.03 when I round off. Okay, so my answer to part 3 of part B of question 2 is that the pH of this solution is 9.03. So to review, first we got the net ionic equation for the reaction between a weak acid and a strong base, which was mentioned in a generic form in topic 8.4 essential knowledge statement. Then we figured out the Kb by doing Kw divided by Ka. We determined the total concentration of the acetate ion. We plugged in the concentration of the acetate ion into the Kb expression, solved for X, which was the concentration of the hydroxide ion, negative log that number, 14 minus that number, and we got pH of 9.03. All right, well, those are all the answers to question 2. Now it is time to move on to question 3. In question 3, it says that aniline, which has the chemical formula C6H5NH2, ionizes according to the equation above. So we can tell that aniline behaves as a base. We can see a Kb for this reaction, and whether it's a strong base or a weak base, hopefully you know the answer to that question. Now, a student is given a solution of aniline and asked to determine the concentration of aniline by titration. So here comes a chemical reaction between aniline and hydrochloric acid. The student uses a solution of hydrochloric acid, HCl, a burette, a flask, an appropriate indicator, and other laboratory equipment necessary for titration. So part A of question 3, write the balanced net ionic equation for the acid-base reaction that occurs between aniline, the base, and hydrochloric acid, which is the acid. So like we saw in question 1, will this be a strong acid, strong base? No. Like we saw in question 2, will this be a weak acid, strong base? No, this is going to be a weak base, the aniline, and a strong acid. So HCl, hydrochloric acid, is on your list of 6 strong acids that you should memorize for the AP Chemistry exam, but strong bases are metal hydroxides where the metal is in group 1 or group 2, and that's not what aniline represents. So aniline is a weak base, and when you see a weak base, whether that's ammonia or aniline or anything else, then that weak base only partially ionizes in aqueous solution. So we write the chemical formula, the molecular formula of that weak base, in this case C6H5NH2. That's the formula of aniline. It's a weak base, so we don't do anything to change that formula. So it's exactly written as it was presented in this question. Now, what about the hydrochloric acid? It's not going to be written as HCl. It's 100% ionized in aqueous solution, so I will split it up into H plus and Cl minus. And if you're thinking, like we saw in question 2 with the sodium ion being a spectator ion, will the chloride ion be crossed off as a spectator ion? Most likely, yes. Let's go ahead and keep going. So what happens is aniline, which is similar to ammonia or methylamine or hydroxylamine or pyridine, it's an example of a weak base in which there is a nitrogen atom and there's a lone pair of electrons on that nitrogen atom, and that's where the H plus will form a bond. So the base is a proton acceptor. Now here is ammonia, NH3. The lone pair on the nitrogen atom in ammonia will react with the H plus, and then that bond breaks in a water molecule, and you get ammonium, NH4 plus, and then you get the hydroxide ion. So now take a look closely at this slide. I'm going to replace ammonia with aniline. And you'll notice it's a very similar structure from the perspective of that nitrogen atom. So this is what aniline looks like. C6H5NH2. So there's the lone pair on the nitrogen atom, and so that is able to be a proton acceptor at that spot. And you would get hydroxide, but you would get the anilinium ion. So C6H5NH3 plus, that's the formula of the conjugate acid of aniline. It's known as the anilinium ion. C6H5NH3 plus. Let's go ahead and put that formula on the right side of the equation. So the weak base has that lone pair of electrons on the nitrogen atom. It accepts the H plus from the strong acid. C6H5NH3 plus, that's the conjugate acid of that weak base. That's called the anilinium ion. And then there's the chloride. So the product of this reaction is soluble in water and should be represented as separate ions. Now, you might be watching this video and saying, how do you know that that was soluble? There's no soluble snap ions like sodium or potassium. Well, this is an acid-base reaction. So on the AP Chemistry exam, you can assume that the majority of acid-base reactions take place in aqueous solution. This is not a precipitation reaction. There's no solid. So let's assume that all of the products of an acid-base reaction are soluble unless the AP Chemistry exam question says something about a precipitate or a saturated solution or a solid. We can assume that the products of a acid-base reaction that takes place in aqueous solution remains aqueous. All right, let's go ahead and cross off that spectator ion. So I see chloride on the left. I see chloride on the right. And so now that is the net ionic equation for the reaction between a weak base and a strong acid. And if you're thinking, have we seen this before, like in an earlier part of the lesson? Yes. So when a weak base reacts with a strong acid, there's the weak base represented as capital B. there's the strong acid. Now, it does say hydronium, but that's similar to H plus in terms of those ions are often used interchangeably. There's my Hb plus, or the conjugate acid ion, and then there's water. So take a look at these two versions of the equation. The difference is if you write hydronium, or H3O plus, then you have to show water on the other side of the equation. Otherwise, if you write H3O plus on the left and you don't put water on the right, then that will not be properly balanced in terms of the number of atoms. So I'm going to show you two possible answers to part A of question 3. Take your choice. If you want to write aniline plus H plus to produce the anilinium ion, that is correct. If you want to show aniline plus the hydronium ion, then on the right side of the equation, you have to show the anilinium ion, or the conjugate acid, plus H2O to make sure all the atoms are balanced. All right, well, that's the answer to part A. Let's go ahead and move on to part B of this question. So now we have some details of the titration experiment. The student titrates a 25 milliliter sample of aniline with a 1.24 molar solution of hydrochloric acid, and the endpoint of the titration is reached after 16.63 milliliters of the hydrochloric acid solution from the burette has been added to the flask. What do we have to do in part B? Calculate the molarity of the aniline solution that was titrated in this experiment. Now, be careful. Watch out for this common mistake. Remember that volume times molarity is moles. So I'm going to go ahead and take A volume, 25 milliliters. I'm going to divide by 1,000. I'm going to take A molarity, which is 1.24 moles per liter, and I'm going to do volume times molarity, which, by the way, this is going to be incorrect. So watch out for this common mistake. There's my volume in liters, so 0.025 liters. There's my molarity as a conversion factor. Here's the problem. Watch out for this common mistake. Just because you see A volume and A molarity doesn't mean that they match up. So as you're watching this video, you might realize that I used the volume of the weak base and I used the molarity of the strong acid. So there are two different solutions in an acid-base titration. You have the weak base, in this case, that's the aniline. You have the strong acid, in this case, that's the hydrochloric acid. So that 25 milliliters is the volume of the weak base. There was another volume, which was 16.63 milliliters, and that was the volume of the strong acid in the burette. Now, do we have two molarities? No, we don't have two molarities because one of them is unknown. In fact, that's what we're trying to find. So calculate the molarity of the aniline. Well, we don't know what that is yet. The molarity of the acid in the burette is 1.24 molars. So here is my message to you. In the rush of trying to hurry up and solve this problem on the actual day of the AP chemistry exam, you're given a titration experiment and you pick the wrong volume or the wrong concentration. So with the titration experiment, when you set up your calculation, make sure to put the correct volume with the correct molarity. So now I'm going to do this correctly. Since I don't know the concentration of the aniline, I'm going to start with what I do know. I know the volume of the acid and I know the concentration of the acid, so I can definitely calculate the number of moles of hydrochloric acid that was added from the burette to reach the endpoint. So I'm going to divide by 1,000, so 16.63 is milliliters. That becomes 0.01663 in liters. 1.24 molar, that means 1.24 moles of hydrochloric acid, so 1.24 moles of HCl for every 1 liter. Now, you may recognize that there is a 1-to-1 ratio in our equation from part A. So there's 1 mole of aniline for every 1 mole of that strong acid. Now, the number I got on my calculator by doing 0.01663 times 1.24 is not only the number of moles of HCl, it is also the number of moles of aniline. This is not my answer to part B, but it gets me closer to my answer. Remember, there's a difference between moles and molarity. So what's the volume of that aniline solution? 25 milliliters, and that would be 0.025 liters. Let's take the moles of aniline, 0.02062. Let's divide by the volume in liters, so divide by 0.025. You'll notice that I didn't round off that number of moles because I wasn't done yet. That's why I'm showing 0.02062 with a little extra precision, a little bit of extra significant figures, okay? 0.02062 moles of aniline divided by 0.025 liters. I will round off to 3 significant figures, and I got, for part B, 0.825 moles per liter. That's the concentration of the aniline based on our titration calculations. Some of you watching this video might say, Mr. Farabaugh, can we solve in part B by doing M times V equals M times V? Like, would that work? And the answer is yes, but just be careful. You can only use what I'm about to show you if you have a 1-to-1 mole ratio between the acid and the base. Now, we do. For many acid-base titrations, we have a 1-to-1 mole ratio between the acid and the base. So to get that number, which was 0.825 moles per liter for your concentration, you could set up the equation like this. Molarity of acid times volume of acid equals molarity of base times volume of base. Again, that only works if you have a 1-to-1 mole ratio between the acid and the base. What's my molarity of my acid in this problem? It's 1.24. What's my volume of acid? 16.63 milliliters. Now, I don't have to convert that into liters. As long as I use milliliters on both the left side and the right side of the equation, then the answer will work out. As long as the units of volume are the same, they could be either both milliliters or both liters. All right, what's my molarity of my base? I don't know yet. What's my volume of my base? 25 milliliters. Now, if I pick up my calculator, it would be 1.24 times 16.63 divided by 25, and yes, I get the same answer either way. So we now have answered question A, part A. We've answered part B. Let's move on to part C of this question. In part C of this question, it asks, do you predict that the solution in the flask at the equivalence point of the titration will have a pH that is less than 7, equal to 7, or greater than 7? Write a balanced net ionic equation to support your prediction. Now, back in question 2, when we had reacted the weak acid with the strong base, the pH was actually slightly greater than 7. It was around 9. So the reason why it was a little bit higher than 7 was because the acetate ion acts like a weak base. Here, we have a weak base reacting with a strong acid. Let's focus our attention on the right side of the equation, C6H5NH3+. That's called the anilinium ion. That is a weak acid. So we had a weak base, which is the aniline. It reacted with a strong acid, and now it produces the conjugate acid. So this anilinium ion is not neutral. It behaves as a weak acid. So part C, do you predict that the pH is going to be equal to 7? No. Is it going to be greater than 7? No, it's going to be less than 7 because the anilinium ion behaves as a weak acid. Now, if you stopped right there on the AP Chemistry exam, you would not earn full credit for your answer because we still have to write a balanced net ionic equation to support your prediction. I wonder where we've seen an example in this lesson of a net ionic equation that would support our prediction. Well, it's right there, okay? From topic 8.4, one of the essential knowledge statements says, if you have a weak base and a strong acid, which is what we have in question 3, and you're at the equivalence point of a titration, in other words, equal number of moles of the weak base and the strong acid, then what you're seeing on this slide, that would be proof that this solution is slightly acidic. So there's the HB plus, or the conjugate acid of the weak base, reacting with water. And not only does it produce the weak base, which is capital B in this equation, there's a little bit of hydronium ion. And so that's why this solution is slightly acidic. So back to our answer to part C. I'm going to write the anilinium ion reacting with water. I will write the weak base, so aniline, and there's the hydronium ion. So that is my net ionic equation, which, again, look how similar it is to what I had shown you in the essential knowledge statement for topic 8.4. So this is the official answer now to part C, and now we are ready to move on to question 4. So hopefully all of the answers to question 3 made sense. This is question 4. In question 4, we have another example of an acid-base reaction. And if you're watching this video wondering which type of acid-base reaction that was covered in the essential knowledge statements for topic 8.4 have we not seen yet? Well, in question 1, we saw an example of a strong acid reacting with a strong base. In question 2, we saw an example of a weak acid reacting with a strong base. In question 3, we saw an example of a weak base reacting with a strong acid. So if you're watching this video and you think, I bet that question 4 will involve a reaction between a weak acid and a weak base, you are correct. Let's go ahead and take a look at the details of question 4. It says that 2 equations are shown below to represent the following. Equation number 1, the ionization of nitrous acid, which has the chemical formula HNO2 in aqueous solution. Now, is nitrous acid on your list of 6 strong acids? No, it is a weak acid, and you can tell. Look at the Ka value. It's 4 times 10 to the negative 4. So I'm going to go ahead and jump down to part A, write the balanced net ionic equation for this acid-base reaction. I'm going to put HNO2 on the left. That's one of the reactants. I'm not going to split it up into separate ions because it is a weak acid. So there's HNO2, which is a weak acid. That's a proton donor. So what is our weak base? Our weak base is represented with equation 2, the ionization of pyridine. So pyridine is very similar to what we saw in question 3. That was aniline. So both pyridine and aniline are examples of weak bases where that nitrogen atom, that is going to be the atom that has that lone pair acting as a proton acceptor. So we now have our HNO2, our weak acid. We have our pyridine, our C5H5N, our weak base. Let's go ahead and react them together. Now on the right side of the equation, if the HNO2 loses H+, then I will have NO2-. And if the C5H5N accepts H+, I will have the pyridinium ion, which is C5H5NH+. So there's the weak acid reacting with the weak base. And on the right side of the equation, we have the conjugate base of nitrous acid, or NO2-, and we have the conjugate acid of the pyridine, the pyridinium ion, which is C5H5NH+. So that is the answer to part A. Let's go ahead and move on to part B of this question, which involves some calculations. In part B, calculate each of the following. We have the value of Kb for the NO2- ion, which is going to act like a weak base. And then we have the value of Ka for the pyridinium ion, which is going to act like a weak acid. Now, earlier in this lesson, I showed you the relationship between Ka and Kb. We're going to use that same relationship to do the calculations in part B of question 4. So remember, on the equation sheet, you can see that Kw is equal to 1 times 10 to the negative 14. Kw is equal to the product of Ka times Kb. So if you know the Ka, you can calculate the Kb, and vice versa. If you know the Ka, you can do Kw divided by Ka, and that will get you the Kb. Or you could flip that around and do Kw divided by Kb, and you can calculate the Ka. We're going to do both of those calculations in part B. So 1 times 10 to the negative 14 divided by the Ka, which is 4 times 10 to the negative 4. And when I do that math, I get 2.5 times 10 to the negative 11. So that is the value of Kb for the NO2- ion. So it's acting like a weak base. We'll do a similar calculation in the next part here. It will be Ka is equal to Kw divided by Kb. So it's 1 times 10 to the negative 14 divided by 1.7 times 10 to the negative 9. And so when I do that math, I get 5.9 times 10 to the negative 6. That is the value of Ka for the pyridinium ion. So we have NO2 minus and we have C5H5NH plus in solution. Now, which of these substances will dominate and affect the pH of the solution? Well, that's what we have to answer in part C. Let's go ahead and take a look at part C. It says you have a 50 milliliter sample of 0.10 molar nitrous acid, and you're combining that with the same volume and the same molarity, so the same number of moles of the pyridine. So 50 milliliters of 0.1 molar pyridine. Is the resulting solution acidic, basic, or neutral? Now, you might think that it's going to be neutral because we have a weak acid reacting with a weak base, but look at those two Kb and Ka values. They're not equal to each other. One of them dominates. So justify your answer by comparing the values of Ka and Kb that you calculated in part B. Which of these two numbers that we just calculated is larger? That's the one that's going to dominate the pH of the solution. Hopefully you can see that 5.9 times 10 to the negative 6 is larger than 2.5 times 10 to the negative 11. So because the Ka value for the pyridinium ion is larger than the Kb value for the NO2 minus ion, then that's what dominates the pH. It is more likely that this solution will be acidic because the Ka value for the pyridinium ion is greater than the Kb value for the NO2 minus ion. So the resulting solution should be acidic. I'm showing how I compared those two values. So the production of the hydronium ion from that weak acid, it occurs to a greater extent than the production of the hydroxide ion from the weak base. Okay, well, those are the answers to question 4. You have now seen in questions 1, 2, 3, and 4 examples of strong acid, strong base, weak acid, strong base, weak base, strong acid, and then now here this was a weak acid and a weak base. We're almost done with topic 8.4. There's 2 more questions left in this packet for topic 8.4, and they are both multiple choice questions. So now let's go ahead and take a look at question 5. In question 5, we are given an acid-base reaction, and it says, what are the relative strengths of the acids and bases in the reaction represented by the equation above? Now, before I examine the details of this acid-base reaction that we were given in question 5, I'd like to show you a couple of topics from earlier units that will help support how we answer question 5. The first topic comes from Unit 4, and that's topic 4.8, Introduction to Acid-Base Reactions. So when an acid or base ionizes in water, the conjugate acid-base pairs can be identified, and then that last part says, and their relative strengths compared. And that's what we have to do in question 5. We have to compare which acid is the stronger acid, and then which base is the stronger base. Now another topic, this comes from Unit 7, talking about equilibrium. This is topic 7.5. Some equilibrium reactions have very large equilibrium constant values, and they proceed essentially to completion, so from left to right. But other reactions have very small K values, and they barely proceed at all, so they would be favored in the opposite direction from right to left. Let's go back and look at the K value that we're given for this reaction in question 5. If we see a large K value, then the products would be favored. And if we see a small K value, then the reactants would be favored. Wow, look how small that K value is. It's 9.1 times 10 to the negative 7. So what does that mean? It means that the reactants are favored at equilibrium. So the K value is less than 1. Now, to show that the reactants are favored at equilibrium, I'm going to draw an arrow from right to left, and that indicates that the reactants are favored at equilibrium. So how do we answer question 5? We have to decide, is HCN the stronger acid, or is HF the stronger acid? Is F minus the stronger base, or is Cn minus the stronger base? So considering that this equilibrium is favored from right to left, favoring the reactants, if the equilibrium in this reaction favors the formation of the reactants from right to left, then that means that HF is more likely to donate H plus in this equilibrium. So HF is the stronger acid. Similarly, equilibrium favoring the formation of the reactants, so from right to left, Cn minus is more likely to accept H plus, so Cn minus is the stronger base. So now that we know that the reactants are favored at equilibrium, we know that HF is the stronger acid, Cn minus is the stronger base, and so that makes choice C the correct answer. HF is the stronger acid, and Cn minus is the stronger base. All right, there's one more multiple choice question that covers topic 8.4. Let's go ahead and take a look at question 6. In question 6, we are given a titration curve, and it says, which of the following molecular equations could represent the reaction used to generate the titration curve shown above? Now, we're looking for an acid-base reaction. So what I did in question 6 is I picked one of these 4 choices that we can throw away immediately and eliminate it because it's not an acid-base reaction. So as you probably know, an acid-base reaction involves proton transfer so that the H plus is transferred from the acid to the base. So if you look carefully, one of these 4 choices involves something that is not an acid-base reaction. So take a look at the 4 choices and you'll see 1, there is no proton transfer whatsoever, and that's an example of an oxidation reduction or a redox reaction. Have you found it? It's choice D. So if you take a look at choice D, that's not the correct answer because NH3, which happens to be a weak base, is not being a proton acceptor at all. And Cl2 is not being a proton donor or an acceptor or anything. So that is an oxidation reduction or a redox. So I'm going to go ahead and eliminate choice D. Now, the other 3 choices, A, B, and C, involve a base reacting with an acid. But we have to choose the correct answer. So I'll start with choice A. Strong base, sodium hydroxide, strong acid, hydrochloric acid. Now, the pH would normally be 7 at the equivalence point of a strong acid, strong base titration. So if you get an exact number of moles of H plus and the exact number of moles of OH minus, they come together and they make water, the pH would be 7 at the equivalence point of a strong acid, strong base titration. And if you look at the middle of that equivalence point, which would be located at 12 milliliters on the x-axis, right there in the middle is a pH that is approximately 6. If you're having a hard time seeing how do you know that the pH at the equivalence point is approximately 6, I'm going to draw some lines on this graph. So strong base, strong acid is supposed to be around pH 7. And so after drawing those lines, you can see that right in the middle of that rapid decrease in pH would be the pH at the equivalence point, and it's around 6. So for a strong base, strong acid, the pH should be 7. So we can eliminate choice A. I'm looking for either a weak acid and a strong base or vice versa, but it's definitely not a strong acid, strong base because the pH is not 7 at this diagram. Okay, so is it choice B or choice C? Strong base, weak acid, so potassium hydroxide and hydrofluoric acid. Weak base, strong acid, that's called methylamine. CH3NH2 is a weak base, and then hydrobromic acid. So which is it? Well, back in the essential knowledge statements, if you have a weak acid and a strong base, like we saw in question 2, then the pH at the equivalence point would be slightly basic. Well, we have a pH of 6 in question 6, so it's not going to be slightly basic. This is what we're looking for. A weak base reacting with a strong acid, at the equivalence point, it would be slightly acidic. So we're looking for weak base, strong acid. So it's not choice B, because strong base, weak acid would have a pH that's greater than 7, but we don't see that on the diagram. Weak base, strong acid, that's what we're looking for, so that makes choice C the correct answer. All right, well, hopefully the answers to questions 1 through 6 all make sense to you, because now we are ready to move on to the review for topic 8.5, acid-base titrations. Here are some essential knowledge statements from the AP Chemistry course and exam description. An acid-base reaction can be carried out under controlled conditions in a titration. A titration curve plotting pH against the volume of titrant added is useful for summarizing results from a titration. At the equivalence point for titrations of monoprotic acids or bases, the number of moles of titrant added, that would be from the burette, is equal to the number of moles of analyte originally present, that would be in the flask. And this relationship can be used to obtain the concentration of the analyte. Now, this is the case for titrations of strong acids and bases as well as weak acids and bases. For titrations of weak acids and bases, it is useful to consider the point halfway to the equivalence point. That is known as the half equivalence point. At this point, there are equal concentrations of each species in the conjugate acid-base pair. So, for example, for a weak acid, the concentration of the weak acid, or HA, is equal to the concentration of the conjugate base, A-. And so because the pH is equal to the pKa, when the conjugate acid and base have equal concentrations, then the pKa can be determined from the pH at the half equivalence point in a titration. Now, at the equivalence point, the pH is determined by the major species in solution. Strong acid and strong base titrations result in a neutral pH at the equivalence point. However, in titrations of weak acids, or weak bases, the conjugate base of the weak acid, or the conjugate acid of the weak base, is present at the equivalence point and can undergo proton transfer reactions with the surrounding water, producing basic solutions or acidic solutions. So that essential knowledge statement that I just read is pretty much a summary of some of the things mentioned in topic 8.4. And then finally, for polyprotic acids, titration curves can be used to determine the number of acidic protons. In doing so, the major species present at any point along the curve can be identified, along with the pKa associated with each proton in a weak polyprotic acid. All right, well, now it's time to move on to the practice for topic 8.5. This is question 7. In question 7, it says, a solution of 0.10 molar NH3, so that is ammonia, that happens to be a weak base. It has a pKb value of 4.8. So that solution of a weak base, ammonia, is titrated with a 0.10 molar solution of HNO3. That happens to be nitric acid, which is a strong acid. So we have weak base, strong acid titration. And the question asks, which of the following correctly identifies the pH of the solution in the flask at the equivalence point of the titration and provides the correct justification? So what happens when you have a weak base and a strong acid? Well, as we saw earlier in question 3 in this packet, it should be slightly acidic when those two chemicals react together. So back in topic 8.4, if you have a weak base, strong acid, and they are equimolar, which means what would happen at the equivalence point of the titration, then the pH will be slightly acidic. And that's because of the behavior of that conjugate acid ion. So if I have ammonia, that would be represented as this capital B, then the ammonium ion, NH4+, represented here as Hb+, that will affect the pH of the solution. So we're looking for less than 7 at the equivalence point when you have a weak base and a strong acid. So back in question 6 of this packet, as well as back in question 3 of this packet, weak base, strong acid, pH is less than 7 at the equivalence point. Now let's go back to look at the 4 choices. Less than 7, so it could be choice A. less than 7, it could be choice B, but let's go ahead and eliminate choices C and D. So the pH of the solution is not going to be equal to 7. That would only happen if you had a strong acid and a strong base. So less than 7 looks like the correct answer is either A or B. Now, the justification in choice A, let's go ahead and do a deeper dive into whether that's correct or not. The justification in choice A says the following. It says the pH at the half equivalence point of this titration is already less than 7. Now, is that a true or a valid justification? Let's go ahead and take a deeper dive into what happens at the half equivalence point. So what I'm going to show you on this next slide, this actually is a diagram from another one of my videos. So from my YouTube playlist that is organized by AP Chemistry CED units, there is a video for topics 8.4 and 8.5. And at the end of that video, I do a series of particulate diagrams for various titrations, and one of them is a weak base, strong acid titration. Let's go ahead and stop at the half equivalence point. So at the beginning, this happens to be ammonia, which is a weak base. There is the 6 particles of ammonia. And if I stop at the half equivalence point, we have 3 particles of ammonia and 3 particles of ammonium. Now look at that pH. That's around 9 at the half equivalence point. So it's not less than 7. Well, when does it become less than 7? When you get to the equivalence point. So we know that the pH at the equivalence point is less than 7, but at the half equivalence point, it's around 9. So it's not less than 7. All right, so back to the details. Is the pH at the half equivalence point of this titration, is it less than 7? I don't think so. Now, the pOH equals the pKb at the half equivalence point in the titration. So therefore, what's the pKb? 4.8. If the pOH is 4.8, then the pH is 14 minus that value, and 14 minus 4.8 is around 9. So the justification in choice A, saying that the pH at the half equivalence point is already less than 7, that's not true. It's actually around 9. So the correct answer to question 7 is not choice A, it's actually choice B. The pH of the solution in the flask is less than 7 at the equivalence point, but here's the reason why. It's because the ammonium ion, which is the conjugate acid of that weak base, the ammonium ion, NH4+, is classified as a weak acid, which affects the pH of the solution. By the way, this was mentioned in topic 8.4. When you have a weak base and a strong acid, it's that presence of that Hb+, in this case the ammonium ion, reacting with water, will produce some hydronium ions, and so that's why at the equivalence point of a weak base strong acid, the pH will be less than 7 or slightly acidic. So correct answer to question 7 is choice B. All right, let's move on to question 8, which is also a multiple choice question. In question 8, it says, 2 different titration experiments are performed in which a 20 milliliter sample of a monoprotic acid at a concentration of 0.10 molar is titrated with 0.10 molar sodium hydroxide. Information about each acid is shown in the table above. And the question asks, which of the following statements correctly compares the volume of sodium hydroxide required to reach the equivalence point in each titration? So as you look at the 4 answer choices, you can see that HCl will require a greater volume of the titrant, the sodium hydroxide, or HClO2 will require a greater volume of sodium hydroxide, or maybe each sample will require the same volume, or in choice D, perhaps we don't know, we don't have enough information because we don't know the initial pH of each acid solution. So let's go ahead and take a look at the details of these 2 acids. I see same volume, same concentration, but different Ka value. Now, are each of these Ka values greater than 1, less than 1? Well, it turns out there's one of each. So HClO2 is an example of a weak acid, and we know this because the Ka value is less than 1. HCl is an example of a strong acid because, well, look at that Ka value. It's very, very large. So if I have a weak acid versus a strong acid, is that going to make a difference in terms of the volume of sodium hydroxide required to reach the equivalence point? And it turns out, no, it's not going to make a difference. And all we care about is the number of moles of the acid. We don't care whether it's strong or weak. All we care about is the number of moles. And here's why. So this is from topic 8.5. At the equivalence point, for titrations of monoprotic acids or bases, it says the number of moles of titrant, so that would be the sodium hydroxide, the number of moles of titrant added is equal to the number of moles of analyte originally present. So it doesn't matter whether it's strong or weak. All you need to worry about is, do I have the same number of moles of acid? Then I require the same number of moles of the titrant or the sodium hydroxide. So each sample of acid, 20 milliliters of a 0.10 molar solution, has the same number of moles. It doesn't matter if one acid is strong or the other acid is weak. Same number of moles of the acid, same amount of titrant to reach the equivalence point of the titration. So that makes the correct answer to question 8, choice C. So it's all about the number of moles of the acid. It has nothing to do with whether the acid is strong or weak. All right, well, that's the answer to question 8, which is choice C. Now let's move on to question 9, also a question involving a titration experiment. In question 9, it says, propanoic acid, which has the chemical formula HC3H5O2, ionizes according to the equation above. A student is given a solution of propanoic acid and asked to determine the molar concentration of the acid by titration. The student uses a standardized solution of 0.420 molar potassium hydroxide, a burette, a flask, an appropriate indicator, and other laboratory equipment necessary for the titration. And the following titration curve was produced when a 15.0 milliliter sample of the propanoic acid solution was titrated. Now remember that earlier in this lesson, I talked about how you have to be careful that there are two different solutions, two different volumes, two different molarities or concentrations, and so make sure that you put the correct volume with the correct concentration. Now, let's see what we know in terms of the volume of the titrant, the potassium hydroxide, that was required to reach the equivalence point. Do you see that rapid increase in pH? And where that occurs along the x-axis, that is the location of the equivalence point. So looks like it's going to be at 20 milliliters of the potassium hydroxide that was added. That's how much potassium hydroxide was required to reach the equivalence point. So do we have two different volumes? Yes. Do we have two different concentrations? Well, not exactly. We know the concentration of the potassium hydroxide, but we don't know the concentration of the propanoic acid. In fact, that's the whole point. We have to determine the concentration of the propanoic acid by titration. So let's go ahead and make a list of what we know for these two solutions. What's the volume of the propanoic acid? 15 milliliters. What's the concentration of the propanoic acid? Well, we don't know yet. That's what we're trying to find. What's the volume of the potassium hydroxide that's required to reach the equivalence point? Well, it's right there on the x-axis. 20 milliliters of potassium hydroxide is required to reach the equivalence point of this titration. And then what is the concentration of the potassium hydroxide? It is listed as 0.420 molar. So let's go ahead and consider how we can calculate the concentration of the propanoic acid. Remember that back in question 3 of this packet, we did M times V, so molarity of acid times volume of acid equals molarity of base times volume of base. And you can only use this if there is a 1-to-1 mole ratio between the acid and the base. And luckily, this is a 1-to-1 mole ratio. So you can see that there's 1 mole of propanoic acid for every 1 mole of potassium hydroxide. This is a monoprotic acid, so it's going to require that 1-to-1 mole ratio between the acid and the base. All right, here we go. Molarity of acid, we don't know yet. Volume of acid is 15 milliliters. Molarity of base is 0.420 molar, and the volume of base required to reach the equivalence point is 20 milliliters. So when I pick up my calculator, this is the math that I'm doing to solve for the concentration of the propanoic acid. 0.420 times 20 divided by 15. And so when I do that math, I get the answer to part A of question 9, which is 0.560 moles per liter. Now, that is the molarity of the propanoic acid. The next thing that we're going to take a look at in part B is what happens at the half equivalence point. So there's our answer to part A, 0.560 molar for the propanoic acid. In part B, it says use the information in the graph to determine the approximate value of the pKa for propanoic acid. So one of the essential knowledge statements for topic 8.5 says that for titrations of weak acids and bases, it is useful to consider the point halfway to the equivalence point. That is the half equivalence point. And so pH equals pKa at the half equivalence point because we have the same concentration of the weak acid and the conjugate base. Now, in my YouTube video that I had mentioned for topic 8.4 and 8.5, I showed particulate diagrams for different titrations. Let's go ahead and stop at the half equivalence point, which would be at point C in this diagram. Now, look at the particle diagram. We have, in this case, the same number of molecules of the weak acid, HA, as we have number of the A- ions. So pH equals pKa at the half equivalence point. So back to question 9. Let's go ahead and find the half equivalence point on this diagram. It's not 20. That's the equivalence point. It would be half of 20. So right there on the x-axis at 10 milliliters, that's the half equivalence point. Now, what's the pH at the half equivalence point? Well, it looks like it's just under 5. So I would say it is approximately 4.9. So the answer to part B, the pH at the half equivalence point is equal to the pKa of this propanoic acid. So that would be 4.9. And now that we know the answer to part B, we can pick up our calculator and figure out the answer to part C. So it says, based on your answer to part B, which is approximately 4.9, calculate the value of Ka for propanoic acid. So how do I get the Ka? It's going to be 10 to the minus whatever that pKa value happens to be. So 10 to the minus 4.9, that's what I'm putting into my calculator. So the Ka is equal to 10 to the minus 4.9, which is 1.3 times 10 to the negative 5. Now, as we move on to part D of this question, you'll see a particulate diagram. So this is part D. It says the following particle diagram is an incomplete representation of the solution in the flask at a certain point during the titration experiment. So it says complete the particle diagram above by drawing in the species needed to accurately represent the relative amounts of the acid, HC3H5O2, that's the propanoic acid, and the conjugate base, the propanoate ion, C3H5O2-. So draw in the species needed to accurately represent the relative amounts of propanoic acid and propanoate ion present in the solution after a volume of 10 milliliters of the titrant, the 0.420 molar potassium hydroxide, has been added. Note that potassium ions and water molecules have been omitted and are not included or not shown in this diagram. So where it would be 10 milliliters of titrant added. Hey, look at that. That's at the half equivalence point. So we know what's special at the half equivalence point. So what's special is that the concentration of the weak acid, or HA, is equal to the concentration of the conjugate base, or A minus. So on that particle diagram, I need the same number of particles of HA as A minus when you're at the half equivalence point. Well, I see 4 particles of the acid, so there should be 4 particles of the conjugate base, and that would be represented as a black circle. So 1, 2, 3, 4. Now, at this point, I have the same number of molecules of HA as A minus, so the answer to part D has now been completed. Okay, there's one more part of question 9, and this time we have to sketch a titration curve. So it says in part E, the student repeats the titration experiment. They use the same solutions of propanoic acid and 0.420 molar potassium hydroxide that was used in trial 1. So what's the difference between trial 1 and trial 2? Instead of 15 milliliters of the propanoic acid, in trial 2, the student titrates a 30 milliliter sample of the propanoic acid. So what we have to do in part E of question 9 is we have to draw the titration curve that would be expected for trial 2 of this experiment. Now, if you change from 15 milliliters of the propanoic acid to 30 milliliters of propanoic acid, you've just doubled the number of moles of that acid. And if you double the number of moles of the acid that is being titrated, then you also have to double the number of moles of potassium hydroxide required to reach the equivalence point. So where is the equivalence point in trial 1? It's at 20 milliliters of titrant added. So what's 20 times 2? 40. So for trial 2, the equivalence point will actually be reached at 40 milliliters, not 20 milliliters. And we're using the same solution, so the initial pH will start at the same value. So I'm going to go ahead and put a little dot on this diagram at the initial pH. I'm going to put the pKa of 4.9 is going to show up at the half equivalence point. So where would a pH of 4.9 show up in trial 2? Well, whatever half of 40 is. So half of 40 is 20. So at around 20 milliliters, there should be a pH of 4.9. I'm going to put a dot right there, just under 5 at 20 milliliters. Now I'm going to try to sketch the titration curve, and I'll follow the same shape of the curve for trial 1. So here I go. It's going to start off like this. It's going to be relatively around pH of 5. And now there's going to be a rapid rise in pH right at the equivalence point. So there it goes, up, 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 and then it sort of levels off. So my sketch of this titration curve is I moved the location of the equivalence point from 20 milliliters of titrant to 40 milliliters of titrant. And then the halfway point is still at around pH of 5. So I've done that. So my answer to question E looks something like this. All right, well, hopefully all of the answers to question 9 make sense to you. And now we have one more question in this packet. So this is question 10. In question 10, it says the following. The reaction between hypochlorous acid and water is represented by the equation above. A chemist sets up a titration experiment in order to determine the Ka value for hypochlorous acid. The chemist uses the following solutions in the titration experiment. So the analyte, the solution that would be in the flask below the burette, is 0.0100 molar hypochlorous acid. The titrant, the solution that is in the burette above the flask, is 0.0150 molar sodium hydroxide. Shown in the graph above is the titration curve that results when a sample of 0.0100 molar hypochlorous acid is titrated with 0.0150 molar sodium hydroxide. And the location of the equivalence point of the titration is marked with a dot on the graph. So it looks like that would be located on the x-axis at 12 milliliters. Now remember, In a titration experiment, an acid-base titration, you have two different solutions, two different volumes, two different concentrations. Let's go ahead and take a look. Do we know the volume of the titrant required to reach the equivalence point? Yes, that's 12 milliliters. Do we know the concentration of that titrant, the sodium hydroxide? Yes, that's 0.0150 molar. So we know everything about the sodium hydroxide. Now, what about the analyte or the hypochlorous acid? Well, we know the concentration, 0.0100 molar. So what do we not know? We don't know the volume of that hypochlorous acid that was used. So it looks like that's going to be what we have to figure out in part A of question 10. Can I use M times V equals M times V? Yes. Molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. So we do have another example of a 1-to-1 mole ratio between the acid and the base. So what's the molarity of the acid? 0.0100 molar. What's the volume of the acid? Well, we don't know. That's what we're trying to find. What's the molarity of the sodium hydroxide, the base? 0.0150 molar. And as we can see from that dot on the titration curve, the location of the equivalence point, it takes 12 milliliters of the titrant to reach the equivalence point. Let's go ahead and put these numbers into our calculator. So the answer to part A would be calculated as follows. 0.015 times 12 divided by 0.01. And so when we do that math, we get the volume of the hypochlorous acid that was used in this titration experiment, and it works out to be 18 milliliters. So that's the answer to part A. Just like we saw in question 9, let's go ahead and focus on the half equivalence point, and we can focus on the half equivalence point where pH equals pKa. Let's move on to part B. Use the information in the graph to determine the approximate value of the pKa for hypochlorous acid. So what's half of 12 would be the location of the half equivalence point. So that's right there. The half equivalence point is at 6 milliliters. Now, what's the pH at the half equivalence point? Well, I would say it's somewhere between 7 and 8. Looks like it's approximately halfway. So I'm going to say it's approximately 7.5. And if the pH is 7.5 at the half equivalence point, then I've just answered part B. pH equals pKa at the half equivalence point, so the pKa is equal to approximately 7.5. How do I get the Ka if I know the pKa? Well, that would be 10 to the minus 7.5. So in part C, based on your answer to part B, calculate the value of the Ka for the hypochlorous acid. So in my calculator, I'm going to do 10 raised to the minus 7.5. So 10 to the minus 7.5 gives me the Ka for hypochlorous acid. So I get 3.2 times 10 to the negative 8 when I did that math. All right, we've answered parts A, B, and C of question 10. Let's go ahead and move on to part D of this question. I think we have to sketch another titration curve. So it says, the chemist conducted another titration experiment with the following solutions. Now, the analyte is not hypochlorous acid. The analyte is HCl. That's hydrochloric acid, which is actually on your list of 6 strong acids. So we have a strong acid, HCl, and it's being titrated with a strong base, sodium hydroxide. So on the following graph, draw the titration curve that would be expected for an experiment in which a 15 milliliter sample of 0.0100 molar hydrochloric acid, again that's a strong acid, is titrated with 0.0150 molar sodium hydroxide, that's a strong base. Now, in addition to your drawing on the titration curve, the location of each of the following should be marked with a dot on the graph below. So what's the initial pH of a 0.0100 molar hydrochloric acid solution? Now remember, when you have a strong acid, it is 100% ionized in aqueous solution, so therefore the negative log of the concentration of the acid will give you the pH. So the negative log of 0.01, that will give us the initial pH of this strong acid solution. So what's the negative log of 0.01? That's a pH of 2. I'm going to put a dot at a pH of 2 on the y-axis, and it's right there at the beginning of the titration experiment. Now, the next part is, what's the pH of the solution at the equivalence point? Remember, strong acid, strong base, we expect the pH to be 7. Strong acid, strong base, pH of 7. But where would you put a dot at pH 7? We don't actually know at the moment the location of the equivalence point. So how do we figure out the location of the equivalence point? Well, let's review. Do we have two different solutions? Yes. Do we have two different volumes? Well, we only know one of them right now, so we're going to calculate the other. Two different concentrations, two different volumes. Here comes another example of M times V for the acid equals M times V for the base. So another example of a 1-to-1 mole ratio between the HCl, the strong acid, and the NaOH, the strong base. Do I know the molarity of the HCl? Yes, it's 0.01 molar. Do I know the volume of the acid? Yes, it's a 15 milliliter sample of the hydrochloric acid. I know the molarity of the sodium hydroxide. It's actually 0.015, but the location of the equivalence point, I don't know exactly where that is, so that's unknown. And when I pick up my calculator to solve for the volume of base required to reach the equivalence point, I will do 0.01 times 15 divided by 0.015. And when I do that math, the volume of sodium hydroxide required to reach the equivalence point, that works out to be 10 milliliters. So I'm going to put a pH of 7 at 10 milliliters of titrant added, so right there. Now I have to sketch the titration curve, but this time it's going to start pretty low at a pH of 2. It's going to stay low for a while, but as I get closer to the location of the equivalence point, you're going to see a rapid rise in pH. So right about there, and it's going to level off at approximately around pH of 12 or so. When I go past the equivalence point, it's going to be around a pH of 12. So I'm going to go ahead and level off right around pH of 12 or so. So I have now sketched the titration curve for a strong acid, strong base titration. So the answer to part D looks something like this. Not only is that the correct answer to part D of this question, it's also the last question in this packet. So now it's time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice is that if you need more practice problems or more information about topics 8.4 and 8.5, you can review the information in my video for these topics, and you'll find a link to that video in the video description area. My next piece of advice is what I normally say during this point in the lesson. Read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations, and with respect to net ionic equations, we saw lots of examples of net ionic equations in topic 8.4, so practice writing the net ionic equations for various acid-base reactions. Now, when you're comparing the Ka values of two different acids, the acid that has the larger Ka value has a conjugate base with the smaller Kb value. So what I'm saying there is that there's an inverse relationship between Ka and Kb, and that comes from that equation that I mentioned where Ka times Kb equals Kw. So a larger Ka would be associated with a smaller Kb for the conjugate base. Now, if you see a question like question 5 in this packet, and you're given the overall equilibrium constant value for an acid-base reaction, then you can compare the relative strengths of the acids and the bases. So for example, suppose you have HX reacting with Y minus, and it produces HY and X minus. How do you know which is the stronger acid and the stronger base in this balanced equation? Well, it's about the equilibrium constant. So if the K, or the equilibrium constant for this reaction, happens to be less than 1, as we saw in question 5, then the reverse reaction is favored at equilibrium, and the stronger acid and the stronger base would be found on the right side of the equation. So that's what we saw in question 5. But on the other hand, if the equilibrium constant K for this reaction is actually greater than 1, well, now the forward reaction would be favored. So where would you find the stronger acid and the stronger base? If the value of K for this reaction is greater than 1, well, you would find them on the left side of the equation. My next piece of advice is, when doing calculations with experimental data from a titration, make sure to match the correct solution volume with the correct solution concentration. And as you've seen many times in this lesson, if the balanced equation for an acid-base reaction has a 1-to-1 mole ratio for the acid and the base reactants, then you can use the following equation as necessary, which would be molarity of acid times volume of acid equals molarity of base times volume of base. My next piece of advice is related to this graph or this diagram or this table. So what you're seeing is that we have a strong acid, hydrochloric acid, and then we have a weak acid, acetic acid, as we saw in question 2 of this packet. And then we have another example of a weak acid, hypochlorous acid, that we saw in question 10. So take a look at the volume and concentration of each acid. I see that each of these 3 samples of acid has the same volume and the same concentration, so they would require the same amount of titrant to reach the equivalence point. So as I had mentioned when I was explaining question 8 in this packet, each sample of acid, if they have the same number of moles of the acid, it doesn't matter if the acid is strong or weak. Same number of moles of acid, same amount of titrant required to reach the equivalence point in the titration. Now look at those 2 weak acids. One of them has a Ka value of 1.8 times 10 to the negative 5. The other has a Ka value of 3 times 10 to the negative 8. So which one of these acids is the weaker acid? Well, the weaker acid is the one that has the smaller Ka value. So HClO, or hypochlorous acid, is a weaker acid than the acetic acid because it has a smaller Ka. Remember, the smaller the Ka, the larger the Kb for the conjugate base. So look at those titration curves. Why is it that for hypochlorous acid, the pH at the equivalence point is actually higher? And so the reason why the pH is higher at the equivalence point for that weaker acid is because of that inverse relationship between Ka and Kb. HClO is the weaker acid, but then the ClO minus is actually the stronger base. So that's why the pH is higher at the equivalence point for that titration. My next piece of advice is be familiar with the appearance and features of various titration curves. Strong acid, strong base, the pH is equal to 7 at the equivalence point because the ions in the solution are neutral at the equivalence point. Weak acid, strong base, the pH equals the pKa at the half equivalence point, and then at the equivalence point, the pH is greater than 7. Why? Because of the following reaction. The presence of that conjugate base in solution, represented as A minus, it reacts with water and it produces a little bit of hydroxide ions, so the pH is going to be greater than 7 because the solution is slightly basic at the equivalence point. Well, what if you have a weak base titrated with a strong acid? Now at the half equivalence point, POH equals PKB. The pH is now going to be less than 7 at the equivalence point because of the following reaction. The conjugate acid, Hb+, reacts with water to produce a little bit of hydronium ions. So it's going to be slightly acidic at the equivalence point when you have a weak base, strong acid. Now, I mentioned that video. At the end of my video for topics 8.4 and 8.5, I do show a series of particulate diagrams. Study these diagrams. They might be featured on the free response or the multiple choice section of the AP Chemistry exam. So if you study these diagrams, each particle diagram represents the relative amounts of the major species present in the reaction mixture during various points during a titration experiment. You will also find a helpful video on particle diagrams at the link shown below. So again, these are included in the video description area. Particle diagrams for acid-base titrations is another helpful resource. Okay, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 8.6 to 8.8. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.